yeah, I was saying the context. Then I'm going to talk about dataset generation. Then what we use as our classifier in our learning system. And then I'm going to talk about the actual thing that I'm here to talk about, the problem and the solution, some results to illustrate what we have found, and then the conclusions. So as I said, this is the PhD work of Cyril. He's right here, so if you have any questions about the actual implementation of all of this, he's the best person to ask. Actually, if you have anything to complement, you can just shout. So the main topic was deep learning for radio. And this is what he did his thesis on. So yeah, he's the boss here. So the specific work here, so he did many things during his PhD, but one of the things that he did was trying to recognize a radio through its RF signature, okay? So that's what we call transmitter identification based on deep learning, and then radio fingerprinting. The objectives were two. We wanted first to create a good data set that could be used not only for us, but also by other people out there using CorteXlab. And the second one was to test a deep learning algorithm based on convolutional neural networks in order to try to fingerprint actual individual radios. Right now, I have to give you a disclaimer. Deep learning for radio is, it's a trendy thing. Everyone is trying to go that way. I have to say that I don't really believe in it for everything. Many people are trying to replace the whole stack with deep learning, and I have my doubts on that. That's my personal opinion, based on what I've seen. So I think that for some things, deep learning can actually do pretty well, especially the ones where you cannot model your problem very easily. But for other things, we have Shannon, Nyquist, we have, all the big theorems in information theory, communications theory, that give us actually pretty good results and pretty good performance. So I don't think it's a one-stop solution for everything. I think that you should actually try to understand what your problem is. Is it too hard to model with traditional methods? And if it is, then you can go towards deep learning. Maybe deep learning will give you a better result, but it's not even guaranteed. So, yeah, that's it. Okay, so what is fingerprinting? So basically what we want is we want to focus on particular characteristics of the radio to identify them individually, okay? It's more or less like the voice of a person, right? When you have a phone call and it's your mother calling, you pick up the phone and she doesn't need to say it's me and her name. You already know it's her, right? Because of the voice. And that's in a very simplistic way, the same thing that we're trying to do here. We're trying to identify the voice of the radio cards and of the radios in general. And in order for that to happen, the radios must have a voice. There must be something that we can extract from the radios or from the signal, which is imprinted onto the signal, that we can actually use to identify them. And the idea is to identify the radios in spite of the ID field that usually the packets carry. Actually, we can actually take them completely out and still be able to identify each individual radio. So why do we want to do that? There are actually several interesting things that we get when we do this kind of fingerprinting. In our case, we were studying the IoT small packet case, where usually when you have a sensor which is trying to transmit, for example, just the temperature, the size of the packet is usually smaller than the size of the ID fields, right? So you're just wasting resources by transmitting that information if you can get it for free onto the signal itself. So that becomes something which is very interesting in terms of spectral efficiency. And the second thing is for the security/privacy context, right? So if we can identify radios, then we can actually validate that these radios are who they claim they are, right? So we can makes spoofing much harder because now we cannot, only verify the ID field, which is there already inside of the packet, but we can also go further and verify if the signature corresponds to that ID field. But there's also a downside to that, which is maybe governments can track individual radios, or even bad actors can actually track individual radios, and then we lose some privacy because now even if we try to change our, for example, MAC addresses, we're still able, people are still able to identify us in spite of all of that, right? So that is a downside of these kinds of things. So I think it's very important to try to understand them and see what are their limitations, and to be able to respond to all of these questions that will naturally arise. So this is more of the mathematical point of view of what we're trying to do. So we have a transmitter, or actually many transmitters. So each one of those boxes over there, they're transmitters, G1 up to Gn, and Gs are the transfer functions of the overall. It's written RF, but just forget that. It's the overall transfer function that we observe while we're transmitting with these radios. Then we have the channel, which can also be seen as a transfer function, right? H. And then we have an RF transfer function as well, which is for each one of these receivers. We're calling them R. And then with respect to all of these received signals Y, we're going to try to classify to try to identify which transmitter PK was the one transmitting at a certain point, okay? So basically what we're trying to do, the channel is always the same. The receivers may be changing or not, as we're going to see during the presentation. So what we want to identify is the RF transfer function, the transmitter transfer functions G. If we can identify each one of them individually, then we can identify the transmitters. Most of you might already be noticing that this is a really hard problem, right? Because you have these transfer functions at the transmitters, but you also have the channels and those at the receiver, which are rotating your signal, distorting your signal in many ways, and that is actually really, really complicated, okay? So let's move on. So basically, I'm talking about transfer functions, but what is this actually in reality? So it's a mix of many things. Some of these things that I'm listing here might not be the things that you're actually observing, but I'm just listing them out. They're not the things that I am trying to observe. Deep learning will try to do its best, but will not tell us what it's doing, right? So it's a black box, and that's the biggest problem of deep learning systems. But we expect it to be learning using one of these things that I'm going to list right now. So in baseband, it could be, for example, your digital filters, delays, jitter, right? In IF, it could be sampling frequencies. It could be D2A converters. Many of these things, filters, so on and so forth. And in RF, it could be your filters, amplifiers, local oscillators, jitter, so on and so forth. So these are the things that we're hoping that might be imprinted onto the signal such that we're able to identify the transmitters. These are the things we're hoping, and these are the things that were actually studied in the literature. So channel effects have been shown to affect a lot the performance of radio identification, and that is quite understandable because now you have the G's times are convoluted to your H's, which are usually just one H. And while that is very interesting, we're not actually focusing on what we want to focus, which is the RF imprint, right? If we get the channel which is imprinted on the signature, then you could already guess that if I change my radio's position or if the overall environment changes, then I'm not able to identify my radio anymore, and that's really bad. And this is some of the things that we're trying to study in this work. But there are other things. Power amplifiers, local oscillators, these have been studied before, and they have been shown to affect. Well, these are not the ones that we're focusing on. We're mostly focused on the channel effects. Okay, so what do we want to do in the end? We want to, we're using the CorteXlab room, which contains 40 radios. I'm going to show it in one of the next slides. And out of these 40 radios, we want to identify 21 of them, which are USRPs, okay? Those are USRPs N2932s, which are equivalent N210s with SBX daughter boards. And we want to do that based fully and solely on IQ samples. So no equalization, no synchronization whatsoever, just raw IQ samples coming directly from the radios. So in order for us to be able to train a neural network, we need labeled data. And that's the first thing that we want to do. We want to produce a data set, which is one of the hardest parts, because now you need to not only transmit, but you need to be able to attach a tag to each one of the transmissions. And then we want to test the learning capabilities with the deep learning algorithm that we're going to use. Okay, so just a little word about Fit CorteXlab. So you know what it is, and this is a little bit of an ad. This is available for everyone, so any one of you want to use it, you can. You just need to ask for an account, and you can use it. But let me say what it is first. You can already see a little bit with the pictures. We have a total of 42, actually. I said 40, but it's 42 radio cards, radio nodes. All of them are SDRs. Most of them are USRPs. Some of them are Pico SDRs made by NewTek, which we are slowly exchanging for more capable USRPs. We also have octoclocks. So these are those small boxes here. It's very hard to read, as I can realize right now by looking at the picture. These octoclocks are connected to some of these USRPs, and we can actually use them to synchronize either in PPS or in reference all of these USRPs. And this is what actually Cyril used for his presentation yesterday. So you have already seen this picture. The second thing about this room is that it's completely isolated from the world. So it's completely shielded, and we have put some absorbers along the walls, but not all of the walls, in such a way that we have about 60 dBs of isolation with respect to the outside world. That means that you can actually experiment in any frequency you want, with any power you want, and that can be given by these USRPs, without any worries of creating interference with respect to the outside world and so on and so forth. But also, this means that this room is, we're claiming that it's reproducible. We're actually running tests to verify that and to be able to prove once and for all that it is. But this is what we have observed. So for the scientific community, that is actually really interesting, because if you're doing, simulations, well, that is, by definition, reproducible. You can run your algorithm, you can change your parameters, run them again, and then compare, right? But with test beds like this one, if you are not able to say that it's really reproducible, what might happen is that if you run your algorithm today with a set of parameters and then run it tomorrow with another set of parameters, you're not really sure if the result you're getting is from the change of parameters or is by, something that happened, maybe some interference or a car that was outside, just close to it, which changed completely the channel. There's no way of saying for sure. So this is one of the greatest advantages of this testbed. And this is something that I think is really cool, and I think that people should be using more, especially if you're using experiments to validate your work. But anyway, if you're interested about this, we can talk afterward. I have many things to say about CorteXlab. Okay, so on top of that, we have robots. So we can actually test mobility. These robots are just like the ones that you can see here. We have 2 of them. They can carry radio cards on their backs. We can define their mobility patterns. So we can actually say how they will roam around inside of the room. And you might need that also for whatever kinds of experiments you want to do. And it's completely remote access. It means that you do not need to come to INSA. Even if you want to come, we will receive you, open arms. You do not need to do that. You can actually work from where you are. The whole thing is automated, so you can just bring your new radio scripts, GRCs or Pythons, and then the system will take care of deploying the whole thing, turning on the radios, turning on the computers, deploying the whole thing, running, and then gathering the results back. So everything is automated. You do not need to do anything. You do not need to go onto this computer, start, go to the other computer, start. Everything is done automatically for you.
Which frequency do the robots use then?
Sorry?
Which frequency do the robots use?
The
robots also are radio controlled, right?
No, they're not radio controlled.
Okay.
They're completely automated. So you define their mobility patterns, and they will do their things until their battery is about to end, and then they go back to recharge. All right, so let's talk about the data set and the data set generation. So here's where I'm going to talk a little bit about GNU Radio. First, I'm going to give you these overview block diagrams, because the GNU Radio flow graph's actually quite complicated, as you will see. So basically what we have is we have one of the nodes which behave as a scheduler, and the scheduler is just taking care of who transmits when. So it's just telling each individual nodes to transmit at a certain moment. We do not support simultaneous transmissions for the moment. Maybe this is something we could try, but I think it's a little bit harder to identify. It's already hard to identify with individual transmissions. I don't think that with concurrent transmissions and with overlap, I think that's much harder. So basically, you have an UDP trigger that is going on to over the network, and those are telling those nodes from 1 to 21 to transmit at a certain moment. So at the same time, we have a receiver, which is also one of those nodes, as you will see in the following. And that one is always receiving. When it perceives that there is a signal, it gets the signal, labels, and stores. Okay? Basically, it works like this. We will assign all of the red ones as transmitters, and then the green one will be a receiver. And we can change the position of who's the receiver and who's the transmitter. This is not representative of what we did, but it's just an example. So, yeah. Now, this is our transmitter. As I said, it's quite complicated, very hard to read. I'm going to go very quickly over it. So, first thing is that we need a way to label our data. So, we are cheating a little bit. We transmit the packet. That is an IoT-like packet that we want to identify the radios with. But we are also transmitting another packet right before, and that packet contains the ID of the radio. So we transmit 2 packets, one, and then it's separated on time, another one. The other one does not contain any identification. That is the one we use to identify, so that is the one which is stored. And the first one is just used for labeling. So basically, what we have is we have an OFDM transmitter part right here. We have a pilot, which is a Z of 2 pilot. And then we have a small packet with just the identification of the radio who's transmitting. And that is actually stacked upon, with this MUX, the actual packet, which is the one in the bottom, which is the one which we use actually to identify these radios. So that is a QPSK simple transmission. We have some options, which I'm going to show in the next slide. So here it's hard to see, but if you look at the block diagram in the next slide and you compare with this, you'll see that everything is there. And then everything is sent to the UHD sync driver, and everything is transmitted. So this is what we have for the actual packet, which is classified. We have three options. The first option is we have a predefined bit sequence, and this sequence is actually there to mimic a preamble, okay? So we said that, okay, what if we can identify just based on the preamble? We also have a random bit source. So sometimes this packet that we are using to identify is completely random, but still modulated QPSK. And then we also tried with a completely random, uniform random source between -1 and 1, which we send directly to the USRP, okay? So those switches are to select which case we are working on, and these are shown afterwards in the results, but it's just for you to understand what we're doing. Now, this is what the signal looks like in the end, in time. So we have zeros in the beginning, so we wait for the N2932 to wake up correctly, stabilize in terms of frequency, all the things. Then we have the preamble, the Z of 2 preamble, also a small guard interval of 40 samples. Then the OFDM header, that is the one that contains the identification. And then we have the payload. Here it's called the payload, but it's actually the packet that we're trying to identify on. And in this case, we have the constant kind of packet. So the payload is 560 samples, more or less, give or take. And we have a little bit of silence in the beginning. Yeah, that's it. So now let's talk about the receiver. So the receiver, basically, this is the simplified version. The complete version you'll see next. It's very complicated. Actually, very heavy, but not very complicated. So you have an USRP receiver. You do the correlation with the Z of 2 sequence. That will give you a time synchronization. We don't care about frequency synchronization, all these things. Actually, these are the things we want to identify on, so we don't care about that. The time synchronization here is only used to be able to properly extract the signal itself. So the perfect timing, the moment to sample, all of these are not important for us. We want to do actually, we want that to be completely random. It's not going to be because of the correlation, of course, but as random as we can. Then we will look at the packet, the OFDM packet, extract the header, and with that header, we will take the payload and store that onto these buckets, which are the ones we're going to use afterward for training. This is what it looks like. I said it's quite heavy. So basically, this is the OFDM part in the beginning. You have this big block. Cyril loves big blocks with lots of inputs and outputs. And each one of these are actually a bucket. So you have 2 file syncs per node, one for the real and one for the imaginary part. And then you have all 21 of them. I tried to make it readable, but it's still not readable. So, but afterward, you will have access to these slides, and then you can zoom and look. I think it's going to be a little bit more readable. Okay, now let's talk about learning. Basically, the gold standard, as far as we know, the gold standard for classifiers are convolutional neural networks. These are the kinds of networks that we use to identify images. So these are the ones that Google, everyone uses to identify images. Basically, what we want to do is we want to transform our packet, raw packet, onto sort of an image, and then feed that directly to the neural network. So we have our 600 samples. Those are the 560 plus 40 of silence that we feed. We will create an image. The image will be basically 2 times the number of samples that we have. So it's 2 columns, one for real, one for imaginary, and then the number of samples. And then we're going to handle the data. So each example is 1 packet. We have 50,000 packets or examples that's for each transmitter. And then we multiply that by 21, all of the the radios, and we'll have that amount of examples in one data set. And then the data sets will be split into 70 training, 10 validation, 20 tests. These are very standard things. Most of the people are doing exactly the same thing. This is the neural network that we're using. So we're using the input. That's the figure or the image. And then we have these convolutional layers, fully connected layers, and afterwards, that's the softmax output, which we use to decide who is transmitting. Okay, so we did the training offline with the GPU, which is also part of CorteXlab. I didn't say that before. We have a big GPU connected with, I think it's 20 gigabits per second, I don't remember, to the nodes. And we can use that online, but we decided to do it offline. 128 examples per batch, and then 30 training epochs. And I'm just concerned about the time. And this is the results we get. So these are the initial results, okay? So here we had only one receiver inside of the room trying to identify each one of the transmitters. Plain is just a simple packet, no changes. Varying, we have varying amplitude, so we have the amplitude which is going up and down. And then robot, we actually had a robot inside of the room without a radio card, just walking around and then shuffling the channel. Actually, the robot is dressed up with a aluminum foil to be very reflective. Seal did that. And in this graph, so in this bar diagram, what we see is we see the accuracy, so how much, how good were we in identifying these nodes when we trained with plain, so this is what we see here, training with plain and then testing with either plain, varying, or robot. And we see that when we train with plain, so just plain transmissions, no amplitude variations, we get 99.8% of accuracy, which might sound very good, but you should always take these results with a grain of salt. That is tainted by the channels a lot, actually. So we're mostly identifying the channels here, and this is actually the motivation for what we're going to do next and the big problem that we had. But it's still interesting to see that we can do pretty well with this. If we did varying, we lose a little bit with the plain, but the other two are very good. And then with the robot, actually we lose a little bit with plain, we lose a little bit with varying, but we still get a very good result with robot, which is interesting, gives some insights, some ideas, but it's not very surprising for us. So now we get to the problem, and this is where the presentation actually starts. So we said that, well, we're actually identifying the channel. How do we get rid of the channel? So the first idea we had was a simple one. Let's use many receivers. So let's switch the receivers. So instead of using just one, for which the path loss is always going to be the same, let's use many receivers. Mix all of the measurements, then create a big data set with that, and then train on that data set and see what happens, right? That was 3 months of misery. Cyril can attest to that. We were clueless about what I'm going to show you next. Complete waste of time. No, it was not a waste of time because we learned all of this that we're presenting right now, so that was interesting. So up until now, what did we have? We were using node 6 as our receiver, all the other ones as transmitters. And everything was well and good, as you saw in the previous results, working perfectly, very high accuracy. So everything is good. Now, what happens is that we wanted to add new radios, right? So create data sets with all the receivers, as I just said, combine everything into a big data set and then train with that. And then try to see if we generalize to this new data set, right? If by using this, everything works. And did not work. Results were very, very bad. So we said, okay, no problem. Let's look into it. Maybe it's just a small thing. Let's check. So we did some tests. And the first test was we did tests on training. So we isolated each one of the individual receivers. So different ones still, but each individual receiver was isolated. And that's what I'm saying, single RX tests, but done over multiple RXs. So first we tried on the same training and testing data sets, and we saw that the results were good, which is not surprising. Okay, so if we train on one data set and we test on the same data set, that's expected to be good. So far so good. Then we crossed data sets. So we trained on one receiver and then tested on another receiver, measured at the same time. And the results were poor. That's expected. If you remember what I showed before, you have so not only the channel, but also the receiver H function, transfer function, is different. So yeah, we expect that to be bad. So okay, so far so good. That's what we were expecting. Now, we trained on the same receiver, but on two consecutive data sets. So we did one first, and then one after. We did that first over the span of 1 day, very poor results. And we said, okay, maybe CorteXlab is not that reproducible as we were thinking. So let's try to shorten that time. So we did one, and then another right after, like maybe, I don't know, 10 minutes after, something like that. Not even that, yeah, even less. And still, we were getting very poor results. And that was weird, because that used to work pretty well. So we were clueless. And it gets even worse, because when we tried that with receiver 6, it worked. So we're like, what the hell? What the hell is going on? People say that an image is worth 1,000 words, so this is how we were feeling. We were clueless. Why does it work for one radio, the one which we were using in the beginning, and not for the others? So that's where we started going into the details and verifying everything to see if there wasn't any problem. So first we tried exchanging USRPs. So we got some of the USRPs that were not able to generalize over time. And then we exchanged that with some replacements that we had. And sometimes it worked, sometimes it didn't. So that didn't answer the question. So Cyril and I, we spent hours and hours and hours on the computer screen looking at packets, raw packets, IQ samples, trying to understand what's happening. And we couldn't find anything that was worth noting. The packets looked the same. Up to our eyes, of course, they look the same. So no visible differences. And then at some point, I don't know, we were in a meeting, the three of us, with the other advisor, and I don't remember exactly who. Maybe it was me, but I don't remember. Cyril says it was not him. Maybe it was me. I said, okay, what if we're sampling this thing wrong? What if there is a synchronization problem, right? It works with some, doesn't work with others, doesn't work over time. Maybe there's a sampling problem. So we started looking into that. I mean, we were clueless. This was about, I don't know, 3 months in. Testing. Nothing was working. So we were clueless. So there are some facts that supported this idea. Actually, the first one is that before starting the multi-RX tests, we installed the octoclocks. Suspicious, right? We didn't relate one to the other because shouldn't have anything. And Cyril, he turned on the external reference clock because he says, it's cool, now we have octoclocks, let's use them. So, and I mean, his reasoning was okay. It's like, it cannot be heard to be synchronized, right? So we tried that. We disabled the external clock, and it all worked. So we were like, okay, now how do we explain that? So basically, we have everything that works, but we still don't know what happened to node 6. So we went down inside of the room and we started fiddling around with the node, and the clock cable was bad. So that was a big problem. Actually, it was a relief, but at the same time, we were not impressed. We were actually a little bit angry because we wasted 3 months on this. But I think that was actually good because that was what allowed us to realize that it was the clock and the synchronization. So this is our hypothesis of what happened. I'm not 100% sure about this. Maybe if you have some other ideas, you can share that with me afterward. But this is what we think happened. So we use the signal to train these receivers, but there were two situations. The first situation is if we have unsynchronized nodes, then we have a random initial sampling moment, which is going to be retained because the sampling speed is always the same. So the radios are seeing samples which are sampled at a certain moment and then kept throughout the length of the packet. However, when we have synchronized nodes, that initial sampling moment is initialized at the beginning of the whole experiment. So all of the packets are sampled with the same delay with respect to the perfect sampling moment, for example. So this essentially means, with respect to the neural network, is that if the neural networks always sees sampling moments which are completely random, then it learns to ignore that. It just says, okay, this is not useful information, so I will try to find something else to learn upon, right? However, if the sampling is always the same for all of the packets, for all of one data set, then it says, this is important, so I'll keep this, right? And the way we notice this is that Sigel did one test where he tried to teach the neural network to learn only one node, and then the two data sets, one synchronized and one not synchronized, and he was able actually to identify the data set, not the node, the data set, through this, which was very interesting.
Two synchronized data sets, one after the other, taken one.
Yeah, sorry, yeah, that's it. So he was able to identify which data set was which.
With just one neuron.
One neuron, yes.
One computation.
That was actually pretty interesting. Okay, so now let's dig a little bit deeper, and I'm about to finish. Oh no, wait. So we did some tests. I'm going to go very fast on this, but you can ask me questions afterward. We upsampled, and then we started playing with the sampling moment. And here we see that for all of these data sets, DS1, 2, 3, and 4, tested on this data set, and then, trained on this data set, and then tested on the same data set, but with a different delay, we got a very good performance when we were aligned, but bad performance everywhere. For the second result, we did that with multiple RXs, and actually, the performance of the neural network goes down to random. It's not able to identify anything anymore, and we are actually off by 3 samples already. We lose complete performance. And then finally, these are crossed, so we tried some different conditions. So synchronization only on the TX, both RX and none. The lines are training, the columns are testing. So we cross-test on all of these variations, and we see that we get good results, of course, none. This is what we were expecting. We still get good results when we train and test with the same conditions. However, when we cross the conditions, the results go bad very, very fast, which actually supports what we were thinking in the beginning. So we're pretty sure that this is what's happening, but maybe some of you might have some other ideas. You're smart people, and if you do, let me know afterwards. So takeaways. So when we create data sets for deep learning for radio, you have to be really careful. This is very critical. I see people creating data sets as if it was like water. Like, let's put some radios to transmit and let's record. That's it, data set. And it's not that simple. You can create lots of data sets, but are they going to be useful? Maybe not, okay? Second thing is that if you have some parameters which seem like it's not going to affect, beware of that as well, because it might actually affect and might affect completely what you have, right? So this is what we observed. Second thing is if you want to synchronize, probably PPS is okay, but if you're using raw packets like we were, make sure that your 10 megahertz ref signal is either turned off or you know what you're doing at least. So this is what I was saying yesterday. People are doing deep learning, like, it's just deep learning. We can do that, no problem. But if you know what you're doing, if you understand the signal processing behind, then you can actually do much better of a job. Finally, keep a logbook of all your changes. That's very important. Had we noticed before that this was going to happen, we would have probably noticed that was, installing Docker clocks was the reason. So that's it. If you have any questions, or maybe we can take them afterwards.
Didn't the USRP of the Node 6 report lack of an external clock?
It doesn't report anything. It's up to you. You actually go onto the UHD block and you say, I want external or internal reference. And it's just that we marked external, but since there was nothing coming from the external port, we had absolutely no idea.